If it's too loud, let me know.
Hello, everyone. It's my pleasure to share this presentation with you. My name is Zichao Xu, and I'm from Yongjiang Laboratory in China. In this talk, I will present our work on spatiotemporal calibration and ground truth estimation for high-precision SLAM benchmarking in extended reality. Extended reality, or XR for short, is actually a broad term that includes VR, AR, and MR. And one key feature of XR is what we call world-locked rendering, which basically means that virtual content stays fixed relative to the physical world as the user moves around. This is really crucial for creating an immersive experience. Now, to achieve this, accurate 6-degree of freedom head pose estimation is essential. And in modern XR devices, this is typically done using SLAM algorithms. So here's a simple example. But when SLAM produces errors, the rendered content is directly affected. And actually, there are two typical types of noise. First, jitter, and second, drift. Both can, noticeably reduce user comfort. So, to ensure a good user experience in XR systems, and also to provide a reliable way to compare and improve SLAM algorithm, benchmarking has become an increasingly important topic in this field. SLAM benchmarking usually involves comparing the trajectory estimated by the device under test. We often call it the DUT, with a high-precision ground truth trajectory. And marker-based optical motion capture systems are commonly used to provide the ground truth, because they can deliver drift-free measurements. Then, error metrics are calculated by comparing the DUT trajectory with the ground truth, typically including absolute and relative trajectory errors, which can also be further decomposed into rotation and translation components. Now, as XR devices demand increasingly higher immersion, the accuracy of SLAM has improved accordingly, which in turn places higher requirements on the precision of the ground truth system. However, current widely used mocap systems have, in fact, shown limitations in meeting these accuracy requirements. The accuracy of mocap is actually limited by two main factors. First, the mocap system and the DUT use independent clocks and reference frames, so spatiotemporal calibration is necessary. And any error here directly introduces rotation and translation errors in the ground truth. Second, although mocap offers good absolute accuracy, its vision-based marker tracking can, in fact, be sensitive to unstable imaging or segmentation, which then causes high-frequency jitter. So, in short, current mocap-based ground truth provides good translation accuracy, but it cannot accurately quantify rotation errors and interframe jitter. Now, these are often overlooked in other SLAM domains, but in XR they are really critical for user experience. And because of this, we often encounter a situation where two XR devices show very similar benchmark results in mocap-based testing, yet the actual user experience feels quite different. This mismatch is basically caused by the limited precision of the ground truth, leading to inaccurate evaluation. Given the high accuracy of state-of-the-art SLAM systems, our goal is to generate mocap-based ground truth with at least half an order of magnitude lower error, covering both absolute and relative errors. So, to achieve this, we propose a method that introduces an auxiliary IMU to compensate for mocap jitter, and integrates mocap, IMU, and DUT data within a MLE framework. This enables efficient multi-sensor spatiotemporal calibration and produces a high-precision ground truth trajectory centered on the DUT. And to our knowledge, this is in fact the first method to achieve all these targets. Now, here's the workflow. The inputs are raw mocap, auxiliary IMU, and DUT pose data. We first initialize the parameters, then build B-splines on manifolds for continuous time optimization. After batch estimation, the algorithm then outputs the spatiotemporal extrinsics and the DUT-centered ground truth trajectory. Finally, to further improve performance, we also introduce a variable time offset model for precise cross-device synchronization and a screw theory-based pose factor to ensure accuracy when processing DUT data with accumulated errors. Next, the top part shows the factor graph used in our continuous time batch estimation, and it basically illustrates how the states are constrained by sensor measurements. The bottom figure highlights a key reason why our algorithm achieves high-precision ground truth, the complementary mechanism between the IMU and the mocap. Here, the blue curve shows mocap data, which provides globally consistent measurements, but introduces high-frequency noise, causing large errors in derivatives. On the other hand, the green curve shows the IMU, which gives robust derivative measurements, but of course drifts over time due to integration. So, as you can see, their characteristics really complement each other, and by combining them, we can effectively balance these errors. We built a benchmarking system to validate our method. First, we visualized the trajectories before and after processing. And as you can see, the raw mocap data showed noticeable misalignment and jitter. But after optimization, our method produces smooth and well-aligned trajectories. What's more, our approach can also be applied to public datasets to generate high-precision ground truth. For example, it works well on visual inertial datasets like TU-MVIU, achieving excellent results. To show the visual impact, we created an AR demo by rendering a virtual cube using ground truth from both a comparison method, P2P-HEC, and our method. With P2P-HEC, the cube shows noticeable high-frequency jitter because it doesn't effectively suppress mocap noise. Also, due to inaccurate calibration, the virtual object drifts when viewed from different angles. In contrast, our method produces a stable cube that stays consistently aligned with the real world, giving a much better visual experience. We also conducted quantitative comparisons. First, we tested the calibration accuracy of the sensors, since this is a key factor that determines the precision of the ground truth. We repeated the calibration multiple times and computed the mean and standard deviation. As you can see in the table above, our method has the smallest standard deviation, which means it achieves the highest repeatability. The figure in the bottom left corner further visualizes this repeatability. Next, we assessed the overall performance by evaluating the precision of the estimated trajectories across different methods. From the bottom right table, it's clear that our method achieves the highest accuracy. And as highlighted by the green markers, our algorithm is the only one that fully meets all the requirements we mentioned earlier. Finally, to show the practical value of our method, we benchmarked 3 commercial XR devices, Apple Vision Pro, MetaQuest 3, and Pico 4, along with the state-of-the-art open-source SLAM algorithm ORB SLAM 3. For this, we used ground truth trajectories generated by both P2P-HEC and our method. As you can see in the bottom table, inaccuracies in the ground truth can have a big impact on benchmarking results, especially for relative error metrics. To make this clearer, the top right plot shows the absolute rotation error over time for AVP. While both methods show similar overall trends, the results based on P2P-HEC exhibit systematic drift and high-frequency jitter. This is caused by calibration errors and mocap noise, which actually hides the real performance of the SLAM system. Since many XR SLAM benchmarks still rely on P2P-HEC-like methods, this highlights a clear need for more accurate ground truth. Our method effectively addresses this by providing high-precision ground truth trajectories, paving the way for reliable benchmarking and supporting the future development of XR SLAM technology. That's all for my presentation. Thank you very much for listening. Our algorithm is also open-sourced on GitHub, and we warmly welcome any further discussion or collaboration.
Okay, so that's the end of the first presenter, and we still have like 3 more to go. So next one, going for the second one, why slow feels fast and feels slow. Okay.
Hello everyone, thank you for attending my talk. My name is Xi. I'm a PhD student from the UNC Chapel Hill. I'm very happy to present our paper, Why Slow Feels Fast and Fast Feels Slow, Evaluating and Predicting Speed Misperception. This is the first work to comprehensively explore the combined influence of key visual cues on the speed perception. Imagine we are immersed in a VR scene, sitting inside a fast-moving car. The vivid visuals makes us feel as if we are truly speeding forward. This example shows how visual information in VR can strongly influence our perception of motion and speed. However, since this sense of the speed is triggered by the visual cues, the visuals can sometimes mislead our perception. To help you better understand this phenomenon of the speed misperception, let's take a look at an example. Let's take a closer look at this driving scene, where the surroundings swiftly pass by us. And let's experience this with a different visual content. Here comes the question. Which one of the motions do you perceive as faster? Based on our user study, 90% of the participants found the first one to be faster. However, the truth is they are at the same speed. So we are wondering that what factors in the visual stimuli is causing our speed misperception in VR and AR. To comprehensively understand how humans misperceive speed in the visual content, we utilize the Gabor patches as our visual stimuli, because their greeting structure closely approximates the receptive fields of the neurons in our human visual cortex. In addition, we adjusted the contrast and the spatial frequency to investigate how these image features influence our speed perception. As an important factor in the foveal and peripheral vision, we also examine the effect of the eccentricity on the speed perception. Moreover, temporal frequency, which determines the velocity of the visual stimuli, plays a crucial role in this research. Overall, we investigate human speed perception across multiple dimensions, including contrast, spatial frequency, temporal frequency, and eccentricity. Our study followed the method of adjustment protocol, where participants adjusted the speed of the center gabor to match the speed of the peripheral gabor to the best of their perception. After they completed the task, we measured the ratio of the speed between the peripheral gabor and the center gabor. This allows us to calculate the ratio of the perceived speed to actual speed, revealing how users misperceive motion under the different visual conditions. We call it perceived speed ratio. Based on our data, we found that people tend to overestimate speed while viewing higher contrast stimuli. Moreover, this increase in perceived speed becomes more pronounced as the spatial frequency increases. However, we observed that the perceived speed ratio decreased with the higher temporal frequency. And similar to the temporal frequency, the effect of the eccentricity on speed perception is significant. The eccentricity reduces perceived speed. Our study provides a systematic understanding of the visual-induced speed perception. Moving forward, we aim to evaluate these effects in more general and complex VR environments. While prior work has investigated the combined effects of the temporal frequency and eccentricity in the VR settings, the stronger effects of the spatial frequency than contrast on speed perception have remained underexplored. So we aim to address this by testing our findings in realistic scenarios. To differentiate with the pilot study and pursue a more generalizable situation, we designed the study in natural VR scenes. As shown, the user experienced a daily walking situation in this study. For the spatial frequency condition, because spatial frequency being an inherent property of the scene content, influenced by the object distribution, texture, and lighting, could not be directly and precisely controlled through post-processing filters. Therefore, we adjusted the spatial frequency by selectively retaining or removing the high-frequency objects from the field of view. And the users sequentially experience the scenes with different spatially frequencies. For the contrast condition, we implemented a camera filter to control the overall scene contrast. As illustrated, users also experience the scenes with the varied contrast. The evaluation study conducted a two-interval forced choice task, letting the user to differentiate the speed variance between baseline scene and the adjusted low spatial frequency or the low contrast scene. Our study spans 3 immersive scenarios in VR, including the walking, driving, and the gaming. The statistical significant results indicates that the participant consistently misperceived the speed as slower in lower frequency and lower contrast scenes. Our experiments confirms that visual content significantly influences perceived speed, demonstrating its generalizability to the immersive VR environments. This has encouraged us to develop a generalizable model to predict the perceived speed ratio, considering the various visual conditions, including contrast, spatial frequency, temporal frequency, and eccentricity. To model the multi-dimensional relationships while encouraging the local smoothness, we selected the radial basis function neural network. For the details of this neural network, please refer to our paper. Therefore, our model can predict the speed perception in different contrast, spatial frequency, temporal frequency, and eccentricities. The proposed model drives us to a couple of potential applications. Firstly, as a VR user, when viewing a dynamic scene, the visual vestibular conflicts may result as cyber sickness and making us feeling dizzy. To address this issue, we could utilize our model and adjust the visual cues to decrease the perceived speed. This approach could potentially compensate the visual vestibular conflict. Other than using our model for post-calc scene analysis, we could also use it for scene synthesis. Adjusting the perceived speed ratio as 1, we can inversely apply our model. And it will tell us in what size of the visual properties we can synthesize our scene to reduce the speed misperception. By knowing the size of the image features with minimum speed misperception, we can synthesize the scene with a certain size of the visual properties, and it could deliver the VR with corrected speed perception. We propose a perceptual guided framework for the speed perception prediction under various visual properties, and demonstrated 2 potential applications. We believe this work leaves many fascinating future directions to explore. For instance, by additional factors, we envision our model can be supplemented as a perceptual metric to enhance our understanding of the speed perception. In addition, a natural next step would be to extend our model into the human-in-the-loop application, such as evaluating the interactive task performance or enhancing navigation guidance. Thank you for attending my talk. I hope you enjoy it.
Okay, so that's the end of the second presentation. We have 2 more to go. And next one is the experience level influence users' credential for avatar animation realism.
Hi everyone, my name is Yudong Huang. I am a PhD student of Illinois Institute of Technology. Today, I'll be presenting our work, Experience Level Influences Users' Criteria for Avatar Animation Realism. In traditional media, such as films and games, people often define realism as a perfect match with reality, which is intuitive. Some existing VR studies also follow this idea. However, while playing VR chat, a social VR application, we observe that users' animations often show tracking errors or motion lag, but people do not suddenly feel that their partner is not really there, nor do they reduce their willingness to socialize. In fact, in our experiment, we argued and found evidence to support that experienced users sometimes consider imperfect VR chat style animations to feel more real than those that perfectly match real-world motion. Let us start with the related work. Social VR is a form of social interaction where users communicate in real time through virtual avatars in immersive 3D environments. Avatars and the way VR is presented give social VR unique features, as shown on the slide. In social VR, users' movement are captured by different types of devices in real time, and then displayed to others in a shared virtual space. This is neither traditional face-to-face communication nor usual online communication through text or video. This is where the so-called imperfect animations are observed. Studying realism in social VR has 2 values. First, users themselves have a desire for immersive experience. Second, a realistic social VR environment can encourage genuine social behavior, which in turn provides psychology and sociology research with a stable and controllable setting. The term realism is ambiguous and sometimes overlaps with concepts such as immersion and presence. In this study, we use the concept of behavioral realism, which we define as whether users believe an avatar's motion is truly controlled by a person. We believe that user experience influences the criteria people use to judge realism. This idea has some support in previous research. Several VR studies have observed that experience can change how people feel when interacting with media. For example, as users become more familiar with VR applications, their sense of comfort tend to increase. Our study focused more narrowly on the perception of realism in avatar animation. Based on existing work, we proposed the following question. First, can users' experience with a specific social VR platform influence their criteria for evaluating avatar animation realism? Second, how do users' criteria for evaluating avatar animation realism change as their experience increases? Third, can specific emotion features be used to enhance the perceived realism or experience of VR chat users? To find out the answers, we designed an experiment where participants with different levels of VR chat experience evaluated animations from different sources. We then compared their rating. In the following sections, we describe the study design in details from the following aspects: animation, task and procedure, and analysis. First, we prepared the three animation styles called source, reenacted, and modified animation. The source animation were refined motion capture animations, representing animations close to real world. The reenacted animations were performed by the experimenter, who mimicked the source animation inside the VRChat using a Meta Quest 3 headset and controllers. The modified animations were made by taking the source animation and adding common imperfections found in VRChat, which we call motion features. Each motion feature was identified by the experimenter and manually implemented in Unity. The video clip shown in the middle is only one of the 6 motion features. There were 8 different activities, such as standing, walking, and running, with 3 animation styles in total and 6 motion features for the modified type. We had 64 unique animations. All the motion features and activity types are shown on the slide. Next, we invited participants to view and rate these animations inside VRChat. The rating instructions was, giving a high score means that you feel like you're watching the motion of a real human user. Each participant rated all 64 animations. The slide here shows the experiment procedure, and the image on the side displays what participants actually saw in VRChat during the rating task. After completing all ratings, participants fill out the questionnaire about their criteria for judging realism and anything they found to be unusual. After collecting the data, we move on to the analysis stage. Our experiment aimed to test 3 main hypotheses. First, participants with less VRChat experience will rate animations with different criteria than participants with more VRChat experiences. Second, participants with more VRChat experience will rate reenacted animation to be more realistic than source animation. Third, modifying source animations with motion features simulating VRChat errors will increase the realism of the animations for experienced VRChat users. We collected the valid data from 37 participants and divided them into 2 ways. First, by usage, which simply compared users with and without VRChat experience. And second, by experience level, which categorized participants into 3 groups. Low experience, which means 0 to 10 hours of playtime. Medium experience, which means 10 to 500 hours of playtime. And high experience, which means more than 500 hours of playtime. Our results are divided into 3 parts. First is usage on realism criteria. We compared the users and non-users on the source and the reenacted animation styles. A clear interaction appeared. Non-users rated the motion capture source animation higher, while users rated the VRChat style reenacted animations higher, which confirms each one. However, the difference among users group alone was not significant, so H2 was not supported at this stage. Questionnaire responses show that non-users emphasize the smoothness and the physical realism, whereas users focus on whether the motion was achievable inside VRChat, reflecting how platform experience shaped their sense of realism. Second, experience level on realism criteria. When we compare the 3 experience groups, a clear trend appeared. Low experience participants prefer the motion capture, the source animation. Medium experience participants prefer the VRChat style reenacted ones, and high experience participants showed no clear preferences. The pattern partly supported H2, suggesting that experience influences how users define realism, but not in a simple linear way. One possible explanation for this trend observed in high experience group is that highly experienced users have seen both types of emotion in VR chat. Their broader familiarity with both style made them more accepting of high quality, motion captured animations, resulting in more balanced rating. As a complement, high experienced participants show strong expertise. We observed that they sometimes gave higher ratings to animations that were uncommon but technically achievable in VRChat. Some even recognized the modified animations as imitation of the reenacted ones and explained their differences from a technical perspective. This kind of reasoning is similar to how users group focus on whether emotion is achievable within the platform. Overall, this suggests that their realism criteria are still closely connected to platform-specific characteristics, which aligns with our theoretical framework. Finally, we examined whether any of the 6 motion features in the modified animations received significantly higher ratings than the source animations. No significant difference was found, so H3 was not supported. In summary, both having and accumulating VRChat experience strongly affect how users judge the realism of avatar animations. Realism is not fixed or purely about matching reality. It depends on users' platform experience. This suggests that matching reality is not the only path to realism, and developers can shape users' sense of realism through consistent design, giving creators more freedom to define their own visual style and culture in virtual world. Thank you for listening to this work. I'd be happy to answer any question.
Okay, so that's the end of the third one. And yeah, just in case, so this is video presentation. So if you have any questions, you can just contact them or go for the Discord. So the next one will be the last one with the half with them. And
Hello everyone. Imagine how technology might bridge millennia-old philosophy and modern audiences. Our work tackles this challenge. Today, I'm excited to share how we transformed this challenge into an opportunity. Our research, titled Heart Flows with Zen, explores how multimodal mixed reality can make abstract, intangible cultural heritage accessible and engaging for modern audiences. I'm Wenchen Guo from the Hong Kong Polytechnic University. First, I'd like to ask, what does Zen culture mean to you? Has it had any impact on your life? As a component of intangible cultural heritage, Zen has an important position in Asian society. However, Zen faces challenges in its dissemination and inheritance. From literature in the fields of computer cultural heritage and cultural digitization, we find that while we've made tremendous progress digitizing tangible heritage, think 3D scanning of monuments, virtual museum, AR tours, intangible cultural heritage, especially abstract philosophies like Zen, remains largely untouched. Our formative survey of 223 participants revealed 3 critical gaps. First, 79.8% had some knowledge of Zen, but younger generations showed significantly less engagement. Second, current access methods are predominantly traditional temple visits, books, TV programs lacking the interactivity modern audiences expect. Third, while 81% expressed interest in technology-driven cultural experiences, only 34% had ever used VR, AR, or MR. This presents a fascinating paradox. High interest, low accessibility. Abstract concepts like emptiness, non-self, and mindfulness resist simple translation into digital experiences. How do you make someone feel the flow of existence or the tranquility of meditation through technology. This challenge led us to three fundamental research questions. First, what design factors truly foster engagement with abstract ICH like Zen? Second, how can we strategically combine design and technology to create immersive Zen experiences? And third, how does our approach compare to existing alternatives? Our approach, based on symbolic analysis, decoding Zen's sensory divided by practice metaphors, and co-design with Zen culture researcher, artists, audiences. This interdisciplinary approach enabled us to translate abstract concepts into tangible experiences. Then we designed and developed the MR system Flowing with Zen. Flowing with Zen integrates four key innovations. First, symbol to design translation maps Zen concepts like impermanence to algorithmic water flows using Perlin noise. Second, non-intrusive sensing through radar matrices and Azure Kinect enables device-free interaction, no headsets required. Third, multimodal scaffolding combines olfactory cues like sandalwood, haptic elements including rough sandstones, and generative visuals. Fourth, embodied rituals transform walking meditation into step-by-step lotuses, projections, and folded hands into wish seal manifestations. This creates what we term physical-digital harmony. The system presents four interconnected scenarios, representing life's philosophical journey. Ephemeral stream uses algorithmic water flows responding to user movement, symbolizing existence's perpetual flux. Sutra rain dissolves ancient texts upon touch, embodying wisdom's impermanence. Seeking blossoms generates lotus projections with each footstep while revealing Pure Land murals through wall interaction. Finally, Nirvana's embraces responds to meditation gestures with cosmic emptiness and sandalwood scent. A brief report on the user study is given below. Our controlled evaluation with 51 participants compared three conditions: our MR system, a VR implementation, and traditional mobile web content. We evaluated user experience dimensions such as satisfaction, interaction quality, and personalization, and also measured their learning performance. For user satisfaction, our MR system significantly outperformed VR in interaction task satisfaction and interaction form preference. Participants appreciated the natural, hardware-free interaction, with many noting that VR controllers created learning barriers and detracted from the meditative experience. Regarding immersion and engagement, MR scored significantly higher than VR. Participants reported feeling more present and connected to the experience. One participant beautifully described the scenario transitions as like a human lifetime, while others interpreted the flowing elements as time passing by or inner consciousness. Importantly, our system demonstrated superior learning outcomes. Knowledge retention tests at 5 and 30 days post-experience showed significant advantages for both MR and VR over traditional web content, with MR maintaining slight advantages over VR in long-term retention. Qualitative feedback indicates that multisensory elements, particularly the scent of sandalwood, along with embodied behavioral participation, such as walking meditation and hands-together gestures, create an authentic meditative experience that strengthens connections to Zen culture. From our findings, we propose 5 transferable design principles for abstract ICH digitization. First, co-design with stakeholders early to decode cultural authenticity. Second, establish symbolic anchoring between traditional metaphors and interactive elements. Third, leverage embodied behavioral design that maps cultural rituals to system triggers. Fourth, implement multi-sensory scaffolding beyond audiovisual stimuli. Fifth, prioritize hardware-agnostic deployment, that reduces technological barriers. These principles extend beyond then to any philosophical or ideological heritage requiring experiential translation. Our work demonstrates that mixed reality can democratize abstract cultural heritage through embodied, accessible experiences. We're currently adapting this framework to Confucian harmony concepts and Taoist Wu-Wei principles. Future development includes cross-cultural validation and LLM-powered dialogue systems for personalized philosophical exploration. Ultimately, we envision transforming abstract ICH into immersive dojo spaces where ancient wisdom becomes lived experience rather than passive observation. Thank you for your interest in our research. We welcome any questions you may have and look forward to discussing them with you.